The second module of our subject DDCO is related to about combinational circuits and sequential circuits. The whole module is only about these two circuits itself. So under combinational circuits, we will be having some manually given equations for which you have to draw the logic diagrams and the circuit diagrams and all. Then you have this your half adder, full adder, half subtractor, full subtractor, multiplexer, demultiplexer, binary coder, decoder, encoder. All this comes under combinational circuits. Only the thing which comes under sequential circuits is your flip flops, SR, JK, D flip flops. So that will be the end part of the module. So coming to the combinational circuit, so before starting about it, we have to know the definition of that. So the definition is quite simple over here. When logic gates are connected together, this I'll explain you with the help of diagram later. So just let us read out the definition. When logic gates are connected together to produce a specific output for certain specified combination of input variables. So it's not that easy to understand directly from the definition. So just let me explain you with one basic example. Suppose we had some equation like f is equals to, suppose ab plus c. So what is the logic diagram for that? This will be your here ab. So this gives your ab. Then you directly can add this with this like that c. So you will get here ab plus c. And suppose you had another equation which is equals to a plus b plus into d. Okay. So this will be a plus b, that into d will be like this, right? This a, b, and this will be your d. So merging this both now we will merge this both logic diagrams. So you would have seen in your classes how ma'am she draws some lines like this. So here we don't have any bar, so we will simply take 3 lines. So this is your lines for A, B and C. So here what we have A, B like this plus C, right? Let me draw it shortly because we need the remaining space. A, B plus C is over. The same thing we have here, A plus B, right? So here again, here I will put R like this, A plus B into D. Now you have to add this both the thing like this, you will get one specific output. So here this output, so this is the definition of the combinational circuit. So here you are adding more than one circuits with each other to get one combination of the circuits. So let us read the definition again. When logic gates are connected together to produce a specified output for certain specific combination of input variables. So this was a schematic explanation, or just to demonstrate you, I explain you in simple way. So the diagram for this is quite simple. You just have to put a box inside, and there will be n number of inputs and m number of outputs. So it can be how many inputs also and many outputs also. In few cases you will be having specific like only one input many outputs, and in few cases you will be having many inputs but only one outputs. So we will be studying about that later. So let us move on with the topic. So here the relationship between input and output of the combinational circuit is given by y is equals to f of x, where again y can vary from y1, y2, y3 so on up to ym. So it's ym, and x can vary from x1, x2, x3 up to so on xn. So this is the basic definition you have to like remember, and if they ask you like for more marks, you can take one example and draw the truth table, K-map and logic diagram for that and explain. So will be doing that now. Suppose you will be receiving some questions like they'll ask you to design a combinational circuit for BCD exceeding three terms. So this is one of the most important questions asked in your exams. So before moving to that, let us solve one simple sum. So what they have given here, so they have said to design combinations, I'll just write like this, which has with 3 input and 3 output. Okay, they didn't specified any output letters here, so you can take your own letters for this. Then what they have given is when the binary input, okay, the binary input is 0 1 2 3, so the output will be same, binary output will be 1 greater than the input. I will explain this to you now itself later after writing the question. And then another thing what I have done, I can say when the binary input, since we have 3 inputs, right, so we will be having 8 variables here. So for 8 things, so we will be having like 0 1 2 3 so remaining is 4 5 6 7. So when the binary input is 4 5 6 7, then output will be 1 less than input. So this is what given in the question. So let us understand this now. So what they have said, so let me explain here. So they said like we have 3 inputs, right. So let us consider that as A, B, C. Then we have 3 outputs, we will keep it as X, Y and Z. Now you know for A, B, C input, just directly you can put your draw the truth table. We know how to draw the truth table for that. Now, so let us see. So this is my 0 value 1, 2, 3. Okay, so this is my 4, 5, 6, 7. Let me divide this part. So what they said, when the input is 0, 1, 2, 3, the output is 1 greater than the input. So 1 greater than this input should be your output. So what will be your output here? So 0. So 1 greater than 0 is 1, right? So you will have here 0, 0, 1 here. For 1 you will get 2. So 0, 1, 0. For 2 you will get 3, 0, 1, 1. For 3 you will get 4, 1, 0, 0. So this is your 1, 2, 3, 4. So 1 greater than the input. So 1 greater than your each input. For 4, 5, 6 and what I said, 1 less than the input. So 1 less than this. For 4, so 1 less than 4 is 3. So again you will have 3 here. For 5, 1 less than 5 is your 4. You will have 4 here. Then you will have for 6 you will have 5 here. And for 7 you will have 6 here. Now so these values are like 1 less than 3, 4, 5, 6. Understood? So this will be our truth table for this. Now see the next step. First from the given question we understood what we had to do. So first we drew this truth table. If you are getting noise in the background, kindly try to ignore. So here for x, now you can see this one whole thing for this one thing, and here one thing, and this one. So we have to draw truth table for these 3 things separately. Okay, so just keeping this diagram aside, so just take a screenshot of this and keep it ready or note it down. So now I will write some lines here so that you can understand. Now from the truth table for x, that down whole thing, I can write that equals to. So see here, you have 0 in the 4th place and 1 in the 4th place. What are those places? 1 is there in 3, 5, 6, 7. So you have to draw the K map, right? So you need the cell number which you have to like draw the K map. So I can write as summation m of 3, 5, 6, 7. Similarly for y, I can write summation m of so it is for 1, 2, 4, 7. And similarly for z, I can do as summation m, it is there on 0, it is not there on 1, it is there on 2, then you have on 4 and then 6. So for these 3 things you have to draw K maps now. So you have to draw 3 K maps, and along with the 3 K maps you have to draw 3 logic diagrams also. So let me just draw a K map here roughly. So 0, 1, 3, 2, 4, 5, 7, 6, 12, 13, 15, 14, 8, 9, 11, 10. So what is this? 3, 5, 6, 7. 3, 5, 6, 7. Oh, I'm really sorry. We will have only 3 variable came up. By mistake, I did for 4 variables. So we'll be having only for 3 variables. So this is for my Z. 0, 1, 3, 2, 4, 5, 7, 6. 0, 1, 3, 2, 4, 5, 7, 6. Okay, so now let us pair one pair like this, another like this, and another like this. So that's a possible way to do. So here we have for 1, 2, then 4, and then 7. As you can see, for y, each of the things are isolated here. This you have to be like mentioned. Now for z, it's 0, 2, and 4 and 6. This should be 1, right? Sorry for that. Okay, so you have one quad like this. Don't try to pair these things. It's not pair, it's quad. Okay. So now what will the expression for this? So you will be having here 0 and 1, 0, 0, 0, 1, 1, 1, 1, 0. So this here you will be having a bar, a, and similarly you have to write there. So for this you will be having common as only d bar, I guess, a, b, c, c bar, sorry. So only expression for your z is equals to c bar now. So but here you have to write expression for each and everything here. So see here, it will be your a, b bar, c bar. So this will be your a bar, b bar, c. So this will be your a, b, c, and this will be your a bar, b, c bar. Now for this what we will be having? So for this we will be having for this I'll write above, or else I'll write here itself. For this we'll be having it from this lines you can see and write here. Then on the common thing is c. So a, c for this, and for this we'll be having a, b. You have to write plus here. Okay. So then again for this you will have only b, c. So your x equals to this, your y equals to this expression, and your z is equals to this expression. So now what you have to do is you have to draw logic diagram for each. Now for this it's very simple. So this is your logic diagram for z. Here c, and here z is equals to c bar. For this you have to draw like many diagrams, and this is also like simple. Now here a, I'll do a, b first, a, b. Now I'll do for BC. So this is BC. Then what we have, an AC. Now for this it will be like a lengthy line. I'll do directly in the board so that you can understand. So keeping this, now what we have to do, we have to suppose for this logic diagram was there, right? So you have to add this logic diagram, this and this, all in one together. That's why you call it combinational circuit. So let us do that. Now as you can see, we have those 3 logic diagrams. I'll try to keep it like this. Now what you have to do, you don't have bar everywhere, but you have bars here. So you have to take lines like this. So this will be for A. Now what you have to do, add one NOT gate like this and draw a big line. That will be for B, I mean A bar. So this is for B. Add one NOT gate and put straight lines. That is your B bar. And for C you have to do the same. Draw one NOT gate. That will be your C bar. C. So like this if you do once. Now for first X. So I have AB plus A. So just take line from here. Make one dot like this. A, B. Then A, C. Then B and C. So be careful that I am taking line from the first line. If you take from second line, that will become a C bar. So that will be a wrong, like you will get wrong values here. If the external whoever collects the paper sees that, he will obviously deduct your marks. And at the end, so again it will take space to draw all these expressions over here which we have A, B bar, C bar. So similarly you have to draw all the logic diagrams for this. At the end you have to draw this, and whatever you get, suppose one big OR gate will get here, and here only you have this NOT gate one line. So that will get directly attached like this. This will come like this, and that will be added in one OR gate. So this is how you add all the circuits for this sum, and at the end you have to draw in the whole big page. Take a new page for that, don't take half page, because you need one complete full page to do this. Neatly you just do that and finish it. So this was one of the questions. So moving on to the important question, which they have a B, C, D. So that you have to write. So they didn't give anything. So just they said B, C, D exceeds 3 terms like that. So how to do that? So let us understand the question first. So design a combinational circuit to convert BCD to excess of 3 code. So what I have done said here. So I won't write the question, I will directly go with the truth table here. So for binary, so this BCD we have 4 inputs and 4 outputs over here. A, B, C, D you can take as 4 inputs, and W, X, Y, Z as your 4 outputs. So let me draw the truth table over here. So here I will be having let me keep it like this. Okay, so A, B, C, D, your 4 inputs, W, X, Y, Z. And remember one thing, every time whenever you implement any sums like this, so the things which they have asked, so for 4 variables, if there are 4 variables in your question, after the value of 9, from 10 to 15, each cell will be always don't care condition. I will show you that here now. So here 0, 0, 0, 0, 4 times, 8 times zeros will come. That's it. We will have one more over here, that is 9. So these values are 0, 1, 2, 3, 4, 5, 6, 7, 8, this is 9. Now from here we should have like till 11, 12, 13, 14, 15, right? So here you will be having all don't care conditions. So this all will be your X, 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 X. Same goes in the output side, all this will be X itself, even in output place. Okay, what is X? That is don't care, and how to do the KMA for don't care is there in the previous playlist of first module in DTCO. So you can go and see that video first to understand this. Now this part, now we know this thing, now this is the normal truth table, and from 9, after 9 till 11, 10 to 15 it will be don't care, we know. This is easy, this is general, right? So according to question, how to get the output now? So main is output itself, right? So how to get the output? So what they have said, exits 3 side. So each output, in the first thing we saw 1 exits the input. So here each thing only 3 will exceed here everywhere. If you want to be easy, from this 3, right, this will come here. That's it, it's not that difficult. So see, this 3 will come in this place, this 4 will come here, this 5 here, like that. Similarly all this thing after 9 will come here, so till 12 it will go. So let us do that. 0, 0, 1, 1, 0, 1, 0, 0, 4, 0, 1, 0, 1, 5, 0, 1, 1, 0, 6. So you need for 7, 0, 1, 1, 1, 0, 7. Now 8, 1, 0, 0, 0, 1, 0, 0, 1 is your 9. So 1, 0, 1, 0, your 10, 1. Now you have to do for 11, 1, 0, 1, 1 is 11, and for 12 this. So now you can see these 3 all this line. So you can see here for W we have, I will just write the equations here now. For W is equals to summation m of, now see here, 5, 6, 7, 8, 9, we have 1. So 5, 6, 7, 8, 9, now plus summation d of 10, 11, 12, 13, 14, 15. Okay, so this is the way you write the equations now. W now for x. So see here, so 1 2 3 4 and then for 9, 1 2 3 4 9 plus summation d is the same for y, summation m of, now see, you have for 0, then 3 4, then 7 8, 0 3 4 7 8 plus summation d is the same. Now for z is equals to, so you have even number again for z here, 0 2 4 6 8, 0 2 4 6 8 plus summation d, the same thing comes here. Okay, now you have to draw the k map for this, for each 4 expressions. After drawing the k map for each 4 expressions, then you have to uh, write draw the what is that, one big lengthy logic diagram also. See, in the previous lecture, like I showed here, we did first like this and then like this, like this. You can directly draw the whole one big line and then directly show in that all these things also. No need to do two times, directly you can do in that things. So now see here, I won't be drawing the k map, I will just show you the k map here itself, which I have done previously. So see here, you have k map here. So one by one I have did the k map here. So this is for z. For z we are obtaining one octet, and this should be for y, this should be for x, and this should be for your w. So here it's not like completely done here. So just see like this and draw the k map, and then one big logic diagram you have to draw. So just do like that. I will go for this another sum, which is if you want you can just see this truth table and equation and do by your own. So I have given you the numbers, right? So this should be easy. I have shown you how to get these numbers. From this it should be easy for you to plot the k map, and how to do k map, it's already been taught in the previous lectures. So just see that once. So there is another similar questions to this, in which they have asked to design a combinational circuit that generates a 9's complement. So you know the complement is the bar of that same term, right? So it is also simple. You have to draw this A, B, C, D, again 4 inputs and 4 outputs, W, X, Y, Z. So what is the thing? Again till 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So till 9 you will be having your numbers. After that you will be having don't care, 10, 11, 12, 13, 14, 15. So same thing you can see here, I have written in my notebook. So these are the values for 9. Till 9 the values are there, and this complete thing is don't care itself here. Even here don't care. So you know a trick in your childhood classes, most probably in first standard or UKG. For 9 table, what we used to do, we used to write 0 to 9 first, then from 9 to 0, like that. The same thing will happen here. So 9's complement. So here you have 0 to 9. Same thing reverse. So first write here one. So 9 to 8 will come here. So just ulta like this, flip it. So you have to come here. So see, you have 0 here, that 0 will go here. 1 like here, 2 it will go there, 3 here, like, or else you can say it as 9 will come here, 8 will come here, 7 will come. Same thing from last to least. This is from 0 to 9. Same thing from 9 to 8, just write here. Remaining are don't case. So what will be your expression for this w here? W is equals to summation m of, now see, you have for 0 1. Now see, don't get confused and take these numbers. You have to take numbers this itself, which are been mentioned here. So 0 1, only 0 1. So it is only 0 comma 1. That's it. Then plus summation d of 10 to 15 whole thing. Then for x, so x you have 0 1 not there. 2 3 4 5 you have for 2 3 4 5. Then for y you have summation m of, let's see, 2 3 6 7. Then for z you have again 0 odd numbers you have this time. Oh no, even it's even again 0 2, again same thing. For z is equals to 0 2 4 6 8, I guess, yeah, plus these are all the same here. Then from these numbers you know how to plot the k map, and then one whole lengthy logic diagram you have to draw. So as you can see here, here is one example for that logic diagram. So this is the same example for complements of that B which we did previously. So we had AB plus AC plus BC for the first sum which we did. So 0 to 4 it's less, than 4 to 8 it's greater that thing. So I added here this AB plus AC plus BC. Then this 4 thing is for your A B bar C bar, A bar B bar C, A B C, A bar B C, and then for your Z. So you just have to draw like this and leave. Yeah, so here you have to draw like this and finish it. Sometimes they ask you to add everything. So sometimes, so this here 3 inputs and 3 outputs, right? So here you won't add this. Previously I said you to add that. That's with respect to mux, demux, and coder, decoder. So here you just leave it. Suppose sometimes you in your combinational circuit you will be having only one output. Though you got you will get 3 outputs like this, but you want to get one output. So what you have to do, you have to just add all these 3 using one OR gate. So that will be only one output. That will be seen later, but for now just remember, don't add the output. So you should be having 3 outputs, so you have to display them like this. This is the best way to display. Take one whole page and neatly, wherever you are taking the connection, now you have to make a dot like this, dot, so that it should be visible. So that will be very easy for the insulator to see and understand. So this is your one part of the thing. So this is it. So in the next lecture I'll explain you about the half adder, full adder, half subtractor, full subtractor, which is very quite easy. If you just study one, the same thing you have to write for the other one. Either one line will increase or one line will decrease, vice versa. That's it. Thank you.